Welcome back to Physics 141 Online. The last topic that we're going to discuss in this part of the course is actually a fairly straightforward application of Newton's second law, and that is the case of rotational equilibrium. Sometimes you'll find entire courses taught on this subject, and it's sometimes called statics. So this special case is encountered when we have an object or a collection of objects that are free to rotate, but because of the forces acting on them, remain at rest. Examples are found in all kinds of structures, buildings, bridges, and all sorts of systems. And like I said, it actually turns out to be relatively easy to analyze these systems and find the conditions, in other words, what forces have to act on them in order that they remain at rest. So, the condition for translational equilibrium is well known to us, right? The sum of the forces that are acting on an object equals zero. And so if the sum of the forces is zero, the acceleration is zero. Now that actually just requires that the velocity remain constant. But if you have a system that starts off with its velocity equal to zero, then it's at rest. Then if the forces all add up to zero, that object will remain at rest. But now that we know about Newton's second law applied to rotational equilibrium, we can write down the additional condition that the sum of the torques acting on an object is equal to zero. And it's these two equations put together that give us all the information that we need to know to solve statics problems. Note that the force equation can have multiple components to it, and it normally will, sometimes just in the x and y direction. Other times you could have more complicated problems where there's also z components to the forces. So, in a particular problem, we usually are given some information about the forces that are acting on an object, such as the object's weight. But then there are other forces, such as might be supplied by cables that are attached to the object, where we don't know the forces, and those are often the unknowns in the problem. And we're going to do several examples, and I will post some examples online so that you can see how to set these problems up. But it's particularly important to remember in these problems that you are free to choose the axis of rotation about which you will calculate the torques wherever you like. You'll get the same answer no matter where you choose to set the axis of rotation. But some choices will make the algebra much easier than others. So pick the one that makes life the easiest. And often that will be a point on the object where several forces act, because we know that if a force is acting along a direction that passes through the rotation axis, then that force provides a torque that's equal to zero. So here's an example, a very typical example that you'll see in homework problems. Imagine that you have a rectangular beam that has mass m2 and length L, and it's supported by a hinge that attaches it to the wall. And so there's a horizontal cable that also attaches it to the wall, but imagine that we have a second mass m1 that's hanging from a cable attached also at the end of the beam. So what we want to do is find the tension in each of the two cables and also the force that's supplied at the hinge. And it's important to realize that a hinge can provide forces along both the vertical and the horizontal direction. It's tempting sometimes to think that the force acting at the hinge is along the direction of the beam, but you can pick lots of cases where you can see that that is not the case. So when you draw in the force diagram, do not draw the hinge force as if it's acting along the beam, because we just don't know that. And often, as in this problem, there will be some sort of geometrical information that tells us here that the beam makes an angle of theta with the horizontal direction. So, because extended objects that have forces acting on them at different points therefore experience different torques from those forces, we don't want to combine, we don't want to take the beam and represent it in a diagram as a mass point. We want to actually draw a force diagram using the entire size of the beam, because it experiences forces at different points. So one of the forces we know, of course, is the weight, the gravitational force that acts from the center of mass directly downward towards the Earth. We also can see that there's a force in the vertical cable, T1, and likewise a horizontal force acting along the horizontal cable, T2. Now the hinge force, as I said, in general, it can provide forces in both the vertical and the horizontal directions, and so some books label these forces with an H because they're provided by the hinge. Others use different symbols, but I will just call them Fx and Fy. And so these are two of the unknowns. So the unknowns in this problem are F sub y, F sub x, T2, and T1. And using the conditions for translational and rotational equilibrium, we should be able to solve for all these forces. So I will finish this problem in class, and you'll have several other problems just like this to use as practice.